Hey, welcome to part 6 of integral calculus. We're going to get into the applications of this. I guess you've been wondering about all these areas and so on. So we're going to have a look now in the next couple of presentation at some applications. So just a little bit of a review together here now. Let's look at this up here. And we've seen this many times before now, where we started to look at the area under the curve, the total distance travelled under a velocity time graph, if you like. That's where we started with Newton's approach to it. And we said, well, if we want to find that area, it would be an infinite sum. So limit is n tends to infinity, the sum of an infinite number of areas of the rectangles. Okay, under that curve, and we established that way back, and we developed this symbol for that. Okay, this is a symbol for that infinite sum, but we then had to go and work out how do you calculate that. Remember, the S is reminiscent or reflecting the fact that you're summing, and this is the height and this is the width in the original derivation. Doesn't mean that exactly there, it's a limit of all that stuff. But then we said, hey, calculus to the rescue, can we actually evaluate this? We said, yeah, we can find a function, the area giving function, whose derivative is the function that we've graphed there. So we had to come back and get the antiderivative, if you like, to obtain this area giving function. We evaluated at one end of the interval minus the other. We established that before. And of course, coming across here, we've had a look at x cubed in an earlier presentation and found that if you just sum the rectangles across the interval, let's do it now. Here's rectangles here, rectangles, all nice positive heights, going to do an infinite number of them. Yeah, that would give a positive area, call it A1. If we kept going though, something happens. The rectangle heights are going downwards there. They have negative heights. And if we kept doing that sum, remember, that's what this dude over here says. It says you're going to sum the areas of an infinite number of rectangles. Hey, these would come out to be negative areas, wouldn't they? That would have a height here, an area here. A2 would be a negative value. So what we established was that you can't just integrate across the interval neg1, in this case to 3, of whatever that function is there, because you effectively would be having some positive areas and some negatives, so the overall definite integral would be a1 minus a2. Please note that definite integral is always this. Okay, irrespective of where the function goes, it may not therefore always imply the total area between the curve and the x-axis. So we've got to watch that something hasn't happened and the rectangles have dipped underneath. So just keep in mind, let's just get rid of all this writing around here and say the fundamental theorem of calculus is this one here, and it is always calculated that way. Please note, it may not always equal, does not equal the area enclosed always. Not always. We said before, take a look at the graph and just check out whether that summing of those areas of the rectangles does give you a positive value in each part of the region there. All right. Well, that's a bit of old hat. We're going to practice that now. But the new stuff, hey, the new stuff is, could you find the area enclosed between two curves? A function y is f of x and a function y is g of x. I think if you put your thinking cap on there, then you'd be able to work out, if you're working with rectangle heights, I think I'll leave this with you because we're going to do it later. You're doing rectangles there under that curve, an infinite number of them, and you're doing rectangles under this one. How do you reckon you get the area enclosed between the two? I don't think it's too hard just looking at those two rectangles I've drawn there. Maybe I'll make it even easier. I'll draw the big one down here, hang on, go back here, let's draw it again. Let's do this one down here under that top function f of x, and where would be the rectangles here under this one? Okay, so what would you do for the enclosed area, do you reckon? Thinking about, in simple terms, the origin of all of this, and here it is back here, just keep in mind, that was our area under the curve, was the limit as n tends to infinity of the sum of an infinite number, therefore, of rectangles areas. Okay. Have you got your head around that? Well, that's a bit of revision. Let's go down now and have a look at some examples. I've taken some screen clippings here from Hayes Publications there, and we're going to go back to basics again. Find the area of the region enclosed by y equals 2x, the x-axis, x is 0 and x is 4. What does that mean? Let's draw the graph. Y equals 2x, it means that area there. Between x is 0, x is 4, and under the curve there. That's what we've been doing. Two approaches. You could look at the geometry. It is a triangle. Half base times height. 16 square units. Let's use calculus because it's exciting. It's the integral from 0 to 4 of 2x with respect to x. That's the area giving function here. What do we have to do? Remember our new notation. We need to find the antiderivative of 2x. What are we going to do? Increase the power by 1, so 1 becomes 2. Divide by the new power, and that's our function in there. So there you are. X squared, and that's our f of b, isn't it? f of x is x squared, and we're going to do f of 4 minus f of 0. And we don't put that in anymore, we're going to put it like that. So we evaluate x squared at 4, so it's 4 squared. X squared at x is 0, it's 0 squared, 16 square units. And they both agree. Two ways of looking at it. You can do it with geometry for many cases, but of course you can't do it with a geometric approach when it's like this, can you? Because there's no actual known geometric shape to describe that area there, or to describe that function, therefore to get the area there. That's not a known geometric shape there. Where we can use geometry, it's often a lot easier and quicker. Calculus is fun though. So let's have a look at the next one. Now, x squared plus 1, the x-axis from 1 to 2. Let's draw the graph, always a good idea. X squared plus 1. We'll show you later on in this presentation how to do it if you're in paper 1, for example, and haven't got the use of a calculator. So it's from 1 to 2, so we have our strip of area here. So it's going to be not a known shape, so we can't use geometry. Integral from 1 to 2 of x squared plus 1. Nothing's below the axis, all the rectangle heights will be positive, so the area is that definite integral there. Okay, so let's integrate it, increase the power by 1, divide by new power. Increase the power by 1, which would be x to the 1 divided by 1. And we evaluated at 2, and then subtract the value at 1. Sticking in 2 in place of x in each of those spots, we get that, putting 1 there. So now, if you're in paper 1 in the IB program, you would have to be able to work with fractions without a calculator. So just check that. 8/3 minus 1/3 is 7/3. 2 take 1 is 1, so it's 1. So it's 7/3 plus 1, 2 1/3 plus 1 is 3 1/3 square units. Just watch this now. Are you comfortable with doing fraction work without a calculator? Just make sure there. Okay, let's go down and do another one, and then it's time for you to have a go. Well, first of all, I've got here, I'll just bring this up a bit, I've got a review of the calculator now. So if you're trying to do that problem on the calculator, this is in run mode, and what would you do in run mode? Well, you go to Options and Calc when it comes up, and you choose the window here, Integral, as I've done there, and you type the function in and the limits. We've done this before, and up comes the answer over here. Okay, What other way can you do it? You can use the graph section on the calculator, graph mode on the calculator. So draw the graph. I've broken this up, and then you'd go shift in here, F5, go G-solve, entering the lower and the upper limits. It shades under the curve, and you get it that way. So there's a couple of different ways of doing it. There's a big advantage in doing it with the graph mode because you can see whether there's any part of the curve that's gone under the x-axis. Okay. All right, let's have a look at a problem now like this and gives you some as well. The area of one arch of the curve y equals sine 2x in the x-axis. So draw the graph of sine 2x, and one arch would go from 0 to pi on 2. So the area would be integral from 0 to pi on 2 of sine 2x. Let's do that. The integral, the antiderivative of sine 2x is minus cos 2x, divide by the derivative of this, which is 2. Let's remember, derivative of sine is friendly, it's just straight cos, but when you come back, it's minus cos. So what's that when you're integrating? From 0 to pi on 2, sub pi on 2 in. First of all, so we've taken the neg half out the front. Cos of 2 times pi on 2 is cos of pi, minus cos of 2 times 0 is 0. Cos of pi, do you remember that? The cos of pi is neg 1, cos of 0 is 1. So it's neg 1 take 1 is neg 2 times neg a half is 1. Just check that. You must know the sines and cosines of common angles. That's explicitly mentioned in the syllabus. All right, are you ready? Let's do some of these now. So there's question 1 and 2. You might select these. Some of these are a bit easy, so you might just select them. And suggesting looking at it geometrically as well as with integration, and checking it with technology. Probably in run mode and in graph mode perhaps would be a good idea. All right, so pause the presentation, have a look. We'll go through and the answers are down below. So let's have a look then at question 3 and 4. Okay, particular emphasis on these harder ones, harder looking ones, with e to the x and ln x and so on. All right, let's have a look at the answers now. Here they are, and just check your work off there as how you're going. Right, let's move on to something a bit new and interesting. Okay, the area between two functions. Did you think about this? And we're going to prove this in a minute, but I think it was pretty obvious. If you're taking two functions and intersecting between 2 points A and B, then the area is the integral of the difference of the two functions. Let's just have a look at that fairly simply from what I said before. We'll do ones that are both above the x-axis. So like this, as you might have guessed, if you do the integral of, let's say the one on top there, f of x, you're looking at rectangles like that, aren't you? And if you took away the ones underneath, then you should get that, just from a basically simple approach. So you can see you sum the rectangles of the tallest one minus the bottom one. We have an issue here, however, if this is under the x-axis. So we're going to prove that in a minute. So the idea, of course, is to find which one's on top minus which one's on bottom, so that you get a positive area. Or you could just take, and this is explicitly mentioned in the course, you could take the modulus, and we'll do that in a minute. Or if the functions are called y upper and y lower, you could say you just take them away. But we'll have a look at all these methods in a minute. Let's look at the proof for this. And I've basically given a rough idea there. So if you move both the curves straight above the x-axis, so you don't have to worry about considering g of x being under the axis, then you can say the integral of f of x plus k. K is in there because we've translated each of them k, so they're both above the x-axis, so that's not a consideration then, that being below or above the axis. So it's the integral of that one minus the integral of this one, isn't it? Because it's in area below this one and minus the area below that one in the middle there. So then if we did that, using the rules for definite integrals. Your k's would disappear, and it's integral of the difference across that region. So that's just what we had a look at casually just a minute ago. So if you take y equals 0, the x-axis, as one of the curves, then the area here is the integral of that, which is 0 minus g of x, using the same idea, or minus the integral. So in other words, you've got to make this a negative, if you like, minus f of x. So I prefer to think of it as the rectangles would now be of positive height. If you did minus f of x, you basically would make them like that, wouldn't you? Okay, so the integral to get that area under there is going to be minus the integral of g of x dx from a to b. Flipping the rectangles up the other way, if you like. Okay, are you ready? I think you need to do some. Let's have a look at some examples here. So they've gone y upper minus y lower, and x squared take 2x. Well, they're talking about upper being 0, the x-axis, and lower being the function. I really would prefer you go straight to this line where you say, I can see the functions underneath, therefore I'm going to put the integral of minus the function, so that the rectangle heights are all positive now. That idea there. Go straight there. I think this is a little bit unwieldy, a little bit redundant there. If you know what the summing means, if you want an area, you must be summing rectangles of positive height, so you've got to multiply it by negative, and effectively you're looking at that function there, or that part of the curve there. Alright, and then you can do that, increase the power by 1, divide by new power, 2's will cancel out, increase the power by 1, divide by new power from 0 to 2, and stick in the numbers. So this is going to be 2 squared minus 2 cubed on 3 minus 0, and we have an answer. So not too bad. We did look at that sort of thing in an earlier presentation. Alright, let's go on, have a look at some more interesting ones. Here's between a line and a curve. So we've got to first of all find where they meet, because it says enclosed. So we'll put the two functions equal to each other, get a quadratic, factorise it, and get the 2 points of intersection. So if we drew the graph, it's from neg 2 to 2, and it's the one on top minus the one underneath. So it's x plus 2 minus, use a bracket, minus the whole function underneath. We've got to watch that and simplify it. Find the antiderivative, increase power by 1, divide by new power, evaluated at 2, that's 8, neg 2, and 8/3, and then neg 2 in there, and same again. So just watch the signs here. Watch out for that minus the numbers in that bracket. Alright, you could check that with technology. Right, the same stuff, isn't it? Just being careful with the functions and the integration there. So let's come up. Find the total area of the region enclosed by the function on the x-axis. So this is a straight function, but watch its graph. Hey, look at this. So you actually have to see to split it into A1 to make it positive, and then this A2, if you integrate it from 0 to 1, would be negative. So let's not do that. Let's go from neg 3 to 0. That's all above the x-axis, so they're okay. Now this end here is underneath, so I prefer students to put plus the integral from 0 to 1 of minus the function. It doesn't matter where that negative goes, okay, but minus the function. In other words, recognising that the rectangles have to have a positive height to represent an area, otherwise it'll come out negative. Or you can put the negative in there, it doesn't matter. Same thing at the end of the day. Okay, so if you do that, you've actually got to find the antiderivative of each part. There we are, increase power by 1, divide by new power, and then be careful, put a negative and then a bracket, and then subbing in carefully, watching this here, look at the signs. So check that, and also check if it's in paper 1, can you do that in fraction land? Let's have a look. This is 11 1/4, neg 11 1/4 is plus 11 1/4, neg is plus 7/12. how do you do that? Well, I would suggest you say, well, a quarter is 3/12 plus that 7/12 is 10/12. So it's 1 and 10/12, 11 and 10/12. Okay, so there are little tricks there working with fractions to make it easier on yourself if you don't have a calculator in that particular paper. So this common denominator idea. All right, let's have a look now. And here's the next little bit. The area between functions f of x and g of x on the interval can be done with, oh, look at this absolute value notation. In other words, take the two functions away, but if you're not sure what's on top of what, then you could just use absolute value. This is with technology only though. So this enables you to do the function without worrying about drawing the graphs and which one to take away from which other one on the interval. So this is explicitly mentioned in the syllabus, the use of absolute value or modulus. So what you do if you're not sure which is on top of which, let's do it in run mode for a start. You go to options and then number, choose number, and then abs, and I've put that, so far I put that in there. And then what you do is to stick your function in there and do the calculation using graph mode here. So this is in graph mode here, and putting number abs in, putting the function in, and then drawing the graph of the function. And can you see here, it's gone above the axis now because we did the absolute value. So the absolute value means if you have a bit below the axis, then it will be given a positive value, the absolute value, the size of the number. So this is a way in which we can avoid doing a graph and or adjusting it. We can do it on the calculator. So we do absolute value in there and come to this. So this is that example up above, example 6, not between two functions. We haven't got actually two functions here, but we are just doing the one across the region so that abs, this sign, means every part of the graph will be made a positive value, and we don't have to worry about negative bits of the area. It's going to do that to all parts. Let's have a look at some problems that you might try yourself. So here we go. You can do these. These are between curves now. There's one there below the axis. So what will you do? You could use absolute value if you're in a paper where you can use the calculator, or use negative of the function. Okay, so just watch the graphs, and of course if you're not sure, you can use absolute value of the function itself or of the difference of the functions there to make sure the regions are going to come out with a positive area. Okay, so there's question 1 to 5, and scroll down in a minute and have a look at the answers. Let's have a look at 6 onwards there. We've got a few here, so just go 6, 7, 8, 9 and 10. Okay, some little puzzles here. Okay, so that's an interesting little question. Okay, and then 11, 12 and 13. Again, talking about whether the integral actually does represent the area. Okay. And then 14, 15 and 16. I'll come down now and show you the answers. So have a look. All right, so there's the first 6. Just check your work. And 7 through 16. Okay, getting some skills now, I hope, getting the idea of checking against this infinite sum of an infinite number of rectangles and their areas there. Keep that in the back of your mind, and it's a lot easier. Okay, look, I hope you've enjoyed the presentation there. What we are going to do now is to go on with some more applications. some kinematics and also some volume. So that's going to be interesting. So I'll catch you a bit later on. Cheers for now.